ESAT is the saturation field at which carrier velocity has dropped to 1/2. I told you in the beginning, right? In short channel, my carrier velocity will either remain at constant value or it starts decreasing when I'm going to increase the electric field. So that is at what field my mobility is dropping, that it's called as ESAT. ESAT is the field strength at which the carrier velocity has dropped to 1/2 of its value. So what is the maximum value? By 2. So that is going to be ESAT. So that is where when the carrier velocity is going to drop, the drain current also is going to drop. And at this point, the drain current will not depend on channel length. Whereas previously in long channel, ID depends on L. But short channel, because ESAT becomes a constant, your ID is independent of L. So the current dependence on the channel length is no more going to be happening. Furthermore, the drain current and the gate source voltage becomes incrementally linear rather than square law. So you can see here ID is proportional to VGS minus VT. It is not VGS minus VT the whole square as it was in long channel regime. So two important things short channel regime we have to understand. The current is going to be independent of channel length capital L, and the drain current and VGS relationship is going to be a linear relationship, and it is not going to be a square law relationship as we have seen in the long channel. So in all modern fabrication methods, so minimum allowable channel lengths are short enough to ensure that this device is going to operate in a safer thing. So short channel devices are available now, but when you are going to use short channel devices, you have to apply the corresponding mathematics for short channel, and you should not use the equation for what is derived for long channel regime. However, there is no requirement that one has to use whether a short channel device for an application or a long channel device. Nobody will say you that I want a device with short channel, I want a MOSFET with long channel. It is up to the designer. That's where your understanding of the device fundamentals comes into picture. The circuit designer will always ensure that, see, when channel length is minimum, the circuit becomes simple, the device becomes easy to fabricate. So generally, everybody will go for a device with a minimum length. So that is going to be the condition. So minimum effective channel length keep on shrinking, of course. When the application and the technology is going to grow, the channel length also keeps on reducing, which is going to make things difficult for us. So reducing channel length will shift your threshold frequency to 30 to 50 gigahertz, enabling high frequency operation of your device. Okay, so this value is offered by so many high performance bipolar processes, and that is why when you compare BJT and MOSFET devices are used mostly in RF applications, which were previously served only by bipolar devices. So completely now, MOS devices have occupied the places where RF devices are being designed at high frequencies, which were once served by BJT or devices made of gallium arsenide technology. Okay, we had so many issues with BJT, but those are all completely eliminated in MOSFET, and though MOSFETs are being the first choice for applications which are in RF domain or high frequency domain. So when the channel length is small, the electric field is going to be it will extend enough so that the threshold is going to diminish. So which will cause increase in the subthreshold current. So when the channel length is small, you have to apply the corresponding concepts of short channel regime. That is what is mentioned in these